The vast majority of living, adult human beings on this planet cannot digest a glass of milk. Not easily, not without discomfort, not without their bodies reminding them in the hours that follow that cow's milk was never meant for them. It is the people who digest it without a problem who carry a mutation, not the other way around. Take a moment to let that idea settle in. What you might consider a biological given, the act of drinking milk, of putting it in your coffee, of pouring it into a glass for a child, is actually the result of a recent, localized genetic transformation that occurred in certain human populations and not in others. A transformation so recent on an evolutionary scale that it feels almost like yesterday. And if you digest it well tonight, it is perhaps because one of your ancestors, 8,000 years ago, maybe somewhere in the plains of northern Europe or in the savannas of East Africa, lived near a herd, and that herd changed their genes. Before going any further, I want to pause for a moment. This documentary travels far across tens of thousands of years, across genomes, fossils, laboratories, and questions that science has not yet resolved, and I would love to know who is listening tonight. You might be in New York, in London, in Chicago, in Montreal, in Cape Town, in Sydney, in Los Angeles, or perhaps somewhere else in the English-speaking world, in a place I haven't even imagined. Tell me in the comments where you are listening from. I am genuinely curious. And I also want to ask you a question related to what we just opened. Do you think humans are still evolving? Not in the vague sense of changing or progressing, but biologically, genetically, in the Darwinian sense. Before this documentary begins to answer, I would love to know your intuition. Write it down in the comments. We will see together how well it holds up to what follows. And if this kind of journey appeals to you, if the idea of understanding your own body through millions of years of history speaks to you, subscribe. There are many other nights like this one waiting for you. Now let us return to the milk. There is an idea that almost everyone carries without questioning it. The idea that human evolution is something that took place in the past, that our ancestors evolved over millions of years. They lost their fur, gained their bipedalism, developed this massive and costly brain, and then at some point something stopped. That we have arrived, that we are the finished product. It is a comfortable idea, and it is false. Not slightly inaccurate, not nuanced at the margins, but fundamentally, deeply, and verifiably false. Human evolution has never stopped. It is acting right now on your cells, on your neighbors, on the children born tonight, in maternity wards all over the world. It acts on human populations just as it acts on all populations of living organisms. Slowly, blindly, without intention, without direction, without destination, and lactose tolerance is one of the clearest proofs we have. Imagine a herder somewhere in what would become, millennia later, the plains of northern France or the steppes of Ukraine. It is about 8,000 years before our era. This man or woman lives with cows, not as ornaments but as resources for survival. The meat, the leather, and the milk, of course. But this milk is processed, fermented into yogurt, into cheese, into kefir. In these fermented products, the lactose is partly broken down by bacteria, making it easier to digest, because like all adults of their time, this herder is lactose intolerant. This is the biological norm for adult mammals. All mammals produce lactase, the enzyme that breaks down lactose, as infants to digest their mother's milk. Then, at weaning, lactase production naturally decreases. This is what happens in cats, dogs, elephants, and chimpanzees, and it is what happened in practically all adult humans 10,000 years ago. Then, something changed in certain lineages. We do not know exactly where or exactly when. Estimates range from 2,000 to 10,000 years before our era, depending on the region. A mutation appeared. A modification of a single nucleotide on chromosome 2 in a regulatory region near the lactase gene. This tiny modification did something simple and revolutionary. It maintained lactase production into adulthood. A mutation, a single change in 3 billion letters of code. And this person, this anonymous ancestor, who carried this mutation for the first time, could drink fresh milk without pain. Does that really count? Does it really make a difference in a world where food is plentiful? Imagine the winters, the famines, the years when the harvest was not enough, when the reserves ran out in February, when children died of malnutrition. A person who can extract calories directly from the raw milk of their cows in the dead of winter, when the granaries are empty, has an advantage that you cannot measure in our era of 24-hour supermarkets. They survive a little better. They reproduce a little more. Their children inherit their mutation, their grandchildren too. Generation after generation, in the populations of herders in northern Europe and pastoralist East Africa, the frequency of this mutation increased. Not because anyone decided it, not because there was a plan, but simply because the carriers of this mutation had, in this specific context with this particular lifestyle, a reproductive advantage, tiny but real. This is natural selection. It is exactly that. And it happened in our species in a past recent enough that some of our ancestors might have seen the pyramids being built. What is remarkable about this story is its geography. Lactose tolerance is not uniformly distributed across the human species. It is concentrated in certain populations and almost absent in others. In Northern Europe, Scandinavia, the British Isles, Northern France, and the Netherlands, about 90% of adults are tolerant. In certain pastoralist populations of East Africa, the Fulani, the Tutsi, the Maasai communities, the rate also reaches high levels, sometimes through mutations distinct from those of the Europeans. In East Asia, in non-pastoralist sub-Saharan Africa, in a large part of the Middle East and South Asia, lactose tolerance remains low, between 10 and 30% depending on the population. It is a genetic map that reflects a cultural map. The peoples who had traditions of dairy farming evolved to take advantage of it. The others did not, and here is what that means in practical terms. If you are of East Asian descent and you feel uncomfortable after eating ice cream or a large glass of milk, you do not have a problem. You simply have the normal biology of an adult primate. It is the people who feel nothing at all who have the mutation. Lactose intolerance is not a pathology, it is the default state. Tolerance is the adaptation. Tolerance is the recent evolution. But lactose tolerance is just one story among dozens, perhaps hundreds. Because if you look at the human genome with modern tools, high-throughput sequencing, positive selection analyses, and comparisons between populations, you see signatures of recent evolutionary pressures everywhere. Regions of the genome where variation has rapidly decreased, a sign that a favorable mutation has spread quickly. Genes that systematically differ between populations raised in different environments. Adaptations to high altitudes, adaptations to pathogens, adaptations to cold, to drought, to population density. Wherever humans have lived for a long time in sufficiently distinct conditions, bodies have begun to change. Not in spectacular ways, not in ways visible to the naked eye usually, but measurable, real, and ongoing. And yet the idea that human evolution has stopped persists. It is taught sometimes implicitly in the way we tell the history of the species. A long journey from the first hominids to us, with a final endpoint somewhere between prehistory and modernity. Why is this idea so stubborn? Partly because evolution is slow on the scale of a human life. You will not see your species evolve. Your children will not see it either. You have to look over generations, over centuries, over millennia. And even then the changes are gradual, statistical, visible only in the data. Partly also because medicine and technology have profoundly changed the conditions in which humans live and reproduce. People who would not have survived in another era survive today, reproduce, and pass on their genes. We can legitimately ask whether natural selection still operates in the same way. But in the same way is not the question. The question is, does it operate? And the answer is yes. It operates differently, with new pressures, new actors, mechanisms that Darwin could not have foreseen. But it operates. Close your eyes for a moment. You are sitting somewhere tonight in a bed on a couch, perhaps in total darkness. And in every cell of your body there is a genome, 3 billion base pairs, a library of staggering precision, copied and recopied for billions of years since the first bacteria in the warm oceans of an ancient Earth. In this genome there are traces, adaptations to environments that your ancestors passed through, mutations that survived because they offered a tiny advantage to someone who lived 1,000 years ago, 5,000 years ago, 100,000 years ago, fragments of DNA that perhaps come from human species we have not yet named. And in this genome right now, there are variations, alleles that you will pass on or not, to children who perhaps do not even exist yet, frequencies that will change in your lineage imperceptibly over generations. You are not the finished product of evolution. You are a step. It is a thought that can be dizzying or soothing, perhaps both. Because if you are a step, if the species is still in motion, still adapting, still reacting to the pressures of the world, then something is still open. The story is not over, and this story tonight we are going to tell from the beginning, from a small bone found in a cave in Siberia, from a fragment of the past that changed the way we understand our fossil selves, from the proof that there were other humans before us, and that they still live in silence, inside our cells. The milk that some of us digest easily tonight comes from a cow that someone kept 10,000 years ago, and in a cave in Siberia, something much older is waiting to be told. Chapter 2, The Cave Bone. That slightly sweet taste bread can take on when you chew it for a long time. That little trace of agriculture in our saliva only tells part of the story. Because before the fields, before the herds, before the recent mutations that redrew our genome, there were other humans, and some of them still live inside us. In 2008, in a cave in the Altai Mountains in Siberia, archaeologists found a bone. A single bone, a fragment of a pinky bone, about 50,000 years old, no bigger than a school eraser. They packed it carefully and sent it to a laboratory in Leipzig, Germany, to the Max Planck Institute for Evolutionary Anthropology, to the team of Svante Pääbo. He had spent his entire career doing one single thing that the scientific community had long considered impossible: sequencing the DNA of human beings who had been dead for tens of thousands of years. DNA degrades, it fragments, it gets contaminated. The simple warmth of a human hand can pollute a fossil sample with modern DNA. For decades, it was believed that reading the genome of a Neanderthal was out of reach. Pääbo had tried anyway. You have to understand what this effort meant. Imagine a text that has been photocopied thousands of times, then cut into millions of tiny fragments, then left out in the rain for 50,000 years. Some fragments have disappeared, others are illegible. Still others have been mixed with fragments of other texts, bacteria, mold, the hands of everyone who touched the fossil since its discovery. Reconstructing the original text from its debris is what Pääbo and his team learned to do. Laboriously, methodically, with mistakes, false leads, entire nights staring at data that meant nothing. When the small bone fragment from the Denisova cave arrived in Leipzig, the team proceeded as usual. Careful drilling of the fragment, extraction of the powder, chemical treatment, sequencing. And what they found looked like nothing they had ever seen. It was not a Neanderthal. It was not a modern Homo sapiens. It was something else, completely other, a third human. An entire lineage of humans who had lived in Asia for tens of thousands of years, crossed paths with Neanderthals, perhaps crossed paths with our direct ancestors, and vanished, leaving behind no known writing, no identified cave art, no abundant fossils, just this bone, and teeth found later in the same cave, and a jaw fragment discovered in Tibet. They were called the Denisovans, named after the cave. And here is what makes this story remarkable. We know almost nothing about the Denisovans as living beings. We do not know what they looked like. We do not know if they spoke, if they made fire, if they buried their dead. We have a few teeth and a genome. But this genome, this fragmentary text reconstructed from the powder of a pinky bone, changed what we knew about ourselves. Because in this genome, Pääbo's team found something unexpected. Sequences that looked like sequences present in the genomes of living humans today. The Denisovans had not just lived, they had left descendants. Not as a separate species, they had disappeared. But their genes had not disappeared. They had traveled. Today, about 3 to 5% of the genome of the people of Melanesia, Papua New Guinea, and certain Pacific Asian populations is of Denisovan origin. These peoples carry in their cells the partial genome of human beings who vanished 50,000 years ago. They carry it because somewhere, at some point, their ancestors and the Denisovans met and had children together. It is an image worth pausing on. Modern humans, perhaps mid-migration toward the Pacific Islands, perhaps in the forests and plateaus of Southeast Asia, crossing paths with human beings who do not look quite like them. Different, perhaps taller, perhaps with more prominent brow ridges, perhaps with different languages, or none at all. And yet, between these two lineages, something close enough that children could be born. Humanity has never been a straight line. It has always been a network. But the story of the Denisovans does not end there, because among the genes inherited from the Denisovans, there is one that stands today as one of the most striking proofs that human evolution is not only ongoing, but that it can take spectacular shortcuts. The gene is called EPAS1. It regulates the body's response to hypoxia, the lack of oxygen. At low altitude, this version of the gene does nothing special. But at high altitude, at 13,000, 16,000, sometimes 20,000 feet, it does something extraordinary. In most humans who climb to high altitude, the body reacts to the lack of oxygen by producing more red blood cells. It is a short-term response that works, but it comes at a cost. The blood thickens, the risk of thrombosis increases, the heart works harder, and for pregnant women living at altitude, babies are born smaller, and perinatal mortality is higher. Tibetans do not have this problem. They live at altitudes where most humans struggle to breathe, and they have done so for generations, with hemoglobin levels that remain comparable to those of people living at sea level. Their hearts do not overload. Their babies are born at a normal weight. They run, work, and live at altitudes that would leave a lowland climber unable to step out of a tent without gasping for air. For years, researchers knew that Tibetans had a unique version of EPAS1. They just did not know where it came from. In 2014, Svante Pääbo and his team compared the Tibetan sequence of EPAS1 with the Denisovan genome. The match was nearly perfect. Tibetans had inherited their high-altitude adaptation from the Denisovans, from human beings who vanished 50,000 years ago, who had perhaps developed this genetic variant for other reasons themselves. Perhaps adapting to the cold of the Central Asian high plateaus, perhaps for reasons we will never understand. And this gene, passed down during an encounter of which we have no written record, allowed a human population to settle and thrive in one of the most hostile environments on the planet. This is what recent human evolution looks like. Not a slow march toward an ideal, but a series of encounters, accidents, unlikely transmissions. A gene from a vanished species crossing tens of millennia to allow children to be born at 15,000 feet of altitude. In good health, breathing normally, it is tempting to think that the story of the Denisovans is that of a defeated, vanished, erased species. But is that really what happened? Here is another way to look at it. The Denisovans contributed to the genome of a species that survived. Their genes, some of them the most useful, the best adapted, were integrated into a broader, more mobile genome, more capable of adapting to varied environments. They live in the bodies of Tibetans at high altitude, in the bodies of Melanesians in the Pacific Islands, in the bodies of humans who perhaps do not know they carry something so ancient. The disappearance of a species is not always a total end. Sometimes it is a dissolution, an integration, a biological legacy that continues to work long after the lineage that produced it has ceased to exist. Svante Pääbo received the Nobel Prize in Physiology or Medicine in October 2022. The Nobel Committee used an unusually strong word in its press release. He had accomplished something that seemed impossible. What was impossible was reading the past, finding enough coherent information in the debris of bones tens of thousands of years old to reconstruct a genomic picture, proving, not theoretically but empirically with data, that human species now extinct contributed to who we are. What this means for the question of human evolution is profound. We are not the product of a single lineage that progressed toward us. We are the product of a network of hybridization, of encounters, of genes that traveled between species that perhaps should not have been able to have children together, and yet did it anyway. And within this network, certain acquisitions proved so useful that they were maintained by natural selection for tens of millennia. We are, genetically, a mosaic. There is something a little dizzying in thinking that a Tibetan today, sitting in a monastery at 16,000 feet, watching the sun rise over the Himalayas, breathing calmly in an air where the oxygen pressure would slowly kill most of us, carries in his lungs, in his blood, in every cell of his body, a genetic gift from a human being who lived and vanished before our species ever painted a single cave. This Tibetan perhaps does not know this. Perhaps he has never thought about it. He simply breathes normally. And in that normal breath, at that impossible altitude, there is a story 50,000 years old. But if the Denisovans bequeathed us precious adaptations, history is not only generous. Because at the same time that we were inheriting from the Denisovans and the Neanderthals, our ancestors were already carrying within them the seeds of a much more baffling transformation. A brain that, for 100,000 years, has been doing something unexpected, shrinking. In the Denisova cave, a pinky bone was enough to reveal a third human, and in our own skulls, something has been diminishing silently, inexplicably, since our ancestors painted the cave walls, and no one is yet entirely certain why. Chapter 3. The Shrinking Skull. That Tibetan gene, housed for 50,000 years in a body that does not know it carries it, is a form of silent inheritance, and the human brain too carries the silence of a change that no one saw coming. Your brain is smaller than that of your ancestors, not slightly, by about 13%. If the brain of a Homo sapiens living 100,000 years ago had an average volume of about 1,500 cubic centimeters, the modern human brain sits between 1,270 and 1,330 cubic centimeters on average. It is a significant reduction, the equivalent in volume of a medium-sized orange, and no one really knows why. Let us start with what we know. The trend has been documented for decades. It is not disputed in its broad outlines. It is the nature and meaning of this reduction that are debated. Paleoanthropologists who have been measuring fossil skulls since the 19th century have regularly noted that human cranial capacity increased for hundreds of thousands of years from the earliest representatives of the genus Homo about 2 million years ago, up to a peak about 100 to 30,000 years ago, and then began a gradual decrease. The human brain first grew, then it started to shrink. Not catastrophically, not in a way you could observe in a room, but measured across a population and across numerous fossil specimens over periods of tens of thousands of years. The trend is there. And it coincides, and this is where it gets interesting, with the period during which humans began to live in increasingly complex societies, to develop elaborate language, to create increasingly sophisticated tools, to practice funerary rituals, to paint caves, to build the first community structures. It is a coincidence that invites reflection. Here is the first hypothesis, the most counterintuitive one. Socialization made the individual brain less important. Before complex language, before dense social networks, Before systems of cultural transmission, each human brain had to, in large part, solve its problems alone or in small groups. It had to memorize, plan, calculate, anticipate in conditions where little information came from the outside. A large brain was a direct, individual, immediate advantage. Then something changed. With language, techniques could be passed down. An individual no longer needed to reinvent the wheel or the bow or the flint-knapping technique with every generation. They learned they inherited a cultural capital that their ancestors had accumulated, and gradually the cognitive weight that each brain had to carry alone grew lighter. In this model, human socialization functioned a bit like a computer network. When computers are connected and can share resources, each individual machine does not need to be as powerful. Intelligence became collective as much as individual, and perhaps a smaller, less energetically costly brain was enough in a dense social network. It is an elegant hypothesis, but it is not the only one. The second hypothesis is less flattering. It relies on what we observe in other animal species that have been domesticated. Dogs have smaller brains than wolves. Domestic pigs have smaller brains than wild boars. Domestic sheep have smaller brains than their wild ancestors. In each case, domestication seems associated with brain reduction, probably because certain costly cognitive behaviors, constant vigilance, autonomous problem-solving, and complex mapping of a territory are no longer necessary when another agent, the human, manages those functions. The bold hypothesis that some researchers have proposed is this: humans somehow domesticated themselves by creating societies with norms, rules, a division of labor, and collective punishment of antisocial behaviors. Humans gradually reduced the selection pressures that favored hypervigilance, autonomous aggression, and individual dominance. This process of self-domestication could have had effects on brain size similar to what we observe in animal domestication. The idea that we tamed ourselves has something deliciously ambiguous about it, halfway between philosophy and biology, between the praise of civilization and a slight unease we cannot quite name. The third hypothesis is colder, more mechanical. A brain is extremely costly to run. It accounts for about 2% of human body mass, but consumes between 20 and 25% of the body's total energy. A larger brain means more calories burned at rest, more glucose, more oxygen, more blood to pump. For hundreds of thousands of years, when humans lived in environments where food was scarce and energy expenditures were high, a large brain offered advantages significant enough to justify this cost. But as humans developed more efficient hunting, gathering, and later agricultural techniques, access to calories improved, and at the same time, perhaps the selection pressure to maintain a massive brain relaxed. In this model, brain reduction is not an impoverishment. It is an adjustment, the result of a lesser selection pressure for maintaining a costly organ in an environment where other cultural, social, and technological strategies had taken over. But there is a problem with all these hypotheses. They are not mutually exclusive, and more importantly, they are not all testable in the same way. A researcher from Flinders University in Australia published an in-depth analysis of available data on human brain reduction in 2023 and concluded something uncomfortable. We still do not know for sure exactly when the reduction began, how fast it happened, or even if it uniformly affects all human populations or if it is more pronounced in certain geographic lineages. Fossil data is fragmentary. Cranial capacity measurements are approximations of brain volume, not the brain itself, and comparisons between periods and between populations carry methodological biases that spark debate. What remains solid is this: the general downward trend over the last 100 millennia is real. Its causes are still up for open discussion. There is something important in this uncertainty. We live in an era accustomed to the idea that science has answers, and evolutionary biology has many, solid, documented, verifiable answers. But it also has its shadows, questions that the data does not yet settle, and the shrinking brain is one of them. This is not an absence of an answer. It is an invitation to remain curious. Imagine a Cro-Magnon, a clumsy and slightly dated term, but speaking clearly. A Homo sapiens who lived in Europe 30 to 40,000 years ago. He painted the caves of Lascaux and Chauvet. He carved figurines out of mammoth ivory. He wore ornaments, organized funerals, built shelters, and he had a larger brain than yours. Not because he was smarter. Brain size is not a direct indicator of intelligence, and brain structure matters as much as volume. But because his environment, his selection pressures, the daily challenges of his life perhaps demanded something different from what your brain must face. You are not smarter than him. You are not stupider. You are adapted to something else. Your brain is smaller, and it processes information in a network of interconnected brains via elaborate language, via external memory systems, books, writing, archives, the internet, which he did not have. It outsources what it does not need to store itself. Is this an improvement? Is it a regression? Do these words even have meaning in the context of evolution? Evolution goes nowhere, it adapts to right now. What is both unsettling and stimulating is that this brain reduction reminds us of something fundamental about the nature of evolution. It does not progress toward an ideal, it has no goal, it responds to pressures. And when the pressures change, bodies change too. Sometimes in directions that our intuition finds counterintuitive. A smaller brain may be the sign of a species better adapted to its social environment, or of a species that has lost something it will never get back. We do not know yet. What we do know is that human bodies change. Not just brains, but jaws too, arteries, teeth. And there is in these small anatomical changes a window into an evolution that is unfolding quietly, beneath the surface of ordinary days. Tonight, in your skull, there is a brain that is the product of millions of years of evolutionary pressures. It is slightly smaller than that of your prehistoric ancestors. It functions within a network of other brains. The voices you heard today, the text you read, this voice speaking to you now in the dark, it is resting. And somewhere in the signals flowing between its neurons tonight, there is still something ancient, something that comes from far away, something that predates all the history you know. Let it rest. The brain that shrinks silently over millennia is only visible in fossils and data. But there is another way to measure evolution in progress, in the health data of thousands of ordinary people living today. And a study started to understand heart disease ended up proving something it wasn't looking for. Chapter 4, The Woman from Framingham. Inside a skull smaller than that of its ancestors, a brain processes the world differently. But this change happened over tens of thousands of years, too slow to be seen in a human lifetime. What follows happened faster, and it was seen. Framingham is an ordinary town in Massachusetts in the United States. About 40,000 residents. Streets lined with painted wooden houses, grocery stores, churches. Nothing to suggest it would become one of the most important sites of 20th century medical science. In 1948, the American government launched a longitudinal study there on cardiovascular diseases. The initial goal was simple: understand why Americans were increasingly dying of heart disease. Thousands of residents were recruited, examined, followed. Their blood pressure, their weight, their cholesterol, their smoking habits, their family histories, all recorded year after year. The Framingham study ended up lasting for generations. It followed not only the first participants but their children, then the children of their children, a multi-generational medical follow-up of remarkable precision. And in the data of this study, 60 years after its launch, an evolutionary biologist from Yale University found something no one was looking for. Stephen Stearns works on the evolution of life histories, how organisms allocate their energy between growth, survival, and reproduction. He asked a simple question while looking at the Framingham data. Is natural selection still measurable in this population? Can we detect differences in reproductive success based on the physical characteristics of the women of Framingham over several generations? The answer was yes. The analyses showed that in this population, women who were slightly shorter, slightly heavier, with slightly lower blood pressure and slightly higher cholesterol had, on average, a slightly higher reproductive success. They had their first child a little earlier. They had slightly more children in total. If these traits are partially heritable, and the analyses suggested they were to some extent, then over 10 generations the women of Framingham would become, on average, slightly shorter, slightly heavier, with slightly later menopause. Not dramatically. The effect is measured in inches and pounds over several centuries. But the rate of this evolution was comparable to the average rates measured in other animal and plant species. It wasn't theory. It was measurement. Here is the woman at the center of this story. Let us say her name is Margaret, a common name in Framingham, in the 1950s. She was examined for the first time in 1955. She is 42 years old. She is slightly shorter than average, slightly heavier, in good general health. She has had 3 children. Her oldest is 21. She doesn't know she is part of a study that has been running for 7 years. She doesn't know that her data will still be analyzed 60 years after her death. She comes in because the doctor asked her to stop by once a year to say hello and let him take her blood pressure. Her grandchildren are part of the 3rd generation of the study, and in the data of those grandchildren, researchers can begin to trace a line. A slightly sloped line that says, natural selection passed through here. This result had a major impact. Not because it proved something dramatic, but because it proved something specific in a contemporary population with real data. The argument against the continuation of human evolution often rested on the idea that modern medicine had neutralized natural selection, that since almost everyone survived childhood in industrialized countries, differential mortality was no longer selecting, that the survival of the fittest no longer applied. What Framingham showed is that selection does not only happen through differential mortality, it also happens through differential fertility. And even in a society where almost everyone survives, people do not all have the same number of children. They do not all have them at the same age. And these differences, if they are partially heritable, are enough for selection to operate. But we have to go further, because the Framingham study shows another thing, perhaps more unsettling. It shows that selection pressures in modern societies do not look like the pressures that shaped our evolution for millions of years. For almost the entirety of the species' evolutionary history, surviving to reproductive age was the primary selection pressure. Those who died in infancy from disease, predation, starvation, or violence did not pass on their genes. It was brutal, direct, powerful. In modern industrialized societies, this pressure is considerably reduced. Infant mortality plummeted dramatically in the 20th century. Most individuals carrying mutations that would have been lethal in another context survive and reproduce. This phenomenon has a name: relaxed selection. Medicine, surgery, antibiotics, vaccines, everything that allows individuals who would not have otherwise survived to live a full life relaxes the pressures that eliminated certain genetic variants. These variants slowly accumulate in the population. Is this an evolutionary catastrophe? Some have claimed it is, and we must name this argument because it has a dark history. Francis Galton, cousin of Charles Darwin, founder of eugenics in the 19th century, had exactly this concern. If medicine allowed the weak to reproduce, the species would degrade. The human race must be improved by deliberate selection. This idea led in the 20th century to forced sterilization programs, to racial policies, to horrors whose memory the world still bears. Naming Galton here is not trivial. It is a reminder that every time someone claims that human evolution is degrading the species and that we must intervene, we are stepping onto ground whose history is soaked in blood. Biology answers this concern on a factual level. Relaxed selection does not degrade the species. It slowly shifts the distribution of genetic variants in the population in directions that are neither good nor bad in themselves, but which reflect current conditions. If those conditions change, selection pressures will change too. What medicine maintains in the population are not flaws. They are variants that were unfavorable in a particular environment, and which might be neutral or even advantageous in another. Evolution knows no value judgments. It does not know what is good or bad, strong or weak, desirable or not. It only knows what reproduces under the conditions of the moment. What is true, however, is that the conditions of the moment have changed in a way that evolution has never encountered in the history of the species. Women in industrialized countries are having their first children later and later, 30 years old, 35, sometimes older. What was biologically exceptional a century ago has become common. If this trend is partially under genetic influence, if certain women have a biology that inclines them more toward later reproduction, then gradually, the genes associated with this biology will become more frequent. Not because anyone decided it, but because women who have their children later now have the means to do so, and that behavior, repeated over generations, is itself a selection pressure. Modernity does not stop evolution, it redirects it. Night falls on Framingham, Massachusetts. In a house somewhere in this ordinary town, a woman watches her children sleep. She is not thinking about evolution. She is thinking about tomorrow, about what she will make for breakfast, about the morning meeting, about the car that needs to go to the shop. In her cells, in the cells of her children, genetic variants inherited from millennia of silent selection continue their journey. They will pass to the next generation, or they won't, according to mechanisms that no one in this house controls or knows. This is how evolution has always worked, in ordinary nights, in houses where people sleep without thinking about genes. But there is another way the past is written into bodies. It passes through the genes themselves, through something more subtle, faster, more baffling, a writing that starvation can trace into the cells of a child who is not yet born, and that this child might pass on, perhaps, to their own children. This is the story of a winter in the Netherlands, and what it left behind. The Framingham data show a natural selection that is measurable, slow, operating in the ordinary lives of people who know nothing about it. But in Amsterdam, another form of inheritance occurred, faster, more direct, and transmitted without touching the DNA sequence itself. Chapter 5. What hunger wrote in the cells. The numbers from Framingham, slightly shorter, slightly heavier, and slightly more fertile, describe an evolution so slow that no human life is enough to see it pass. But the winter that fell on the Netherlands in 1944 produced something different. Something more immediate, something that still lasts. The hunger winter. Between November 1944 and May 1945, under Nazi occupation, a large part of the Netherlands, Amsterdam, The Hague, Rotterdam, Utrecht suffered a food blockade. The Germans had banned food transports in retaliation for a strike by Dutch railway workers who had supported the Allied landings. The result? About 4.5 million people reduced to a daily ration that fell, at the worst of the famine, to less than 400 calories a day. The normal ration for an active adult is about 2,000 to 2,500 calories, 400 calories. That is a slice of bread, a potato, a little sugar beet. That is all. For months, tens of thousands of people died, the most vulnerable first, the old, the sick, the infants. But thousands of pregnant women survived. They carried their pregnancies through this famine, fed themselves on whatever they could find. Tulip bulb flour, when the grain was gone, potato peels, weeds, and they brought children into the world. These children born of the famine grew up, grew old, and 60 years later, they agreed to participate in medical studies. What researchers found was unexpected. The children of the hunger winter, those who had been conceived or carried during the most severe months of the famine, had, compared to their brothers and sisters, born before or after, significantly higher rates of obesity, type 2 diabetes, and cardiovascular disease. Their metabolism seemed programmed to store, to hoard, as if every cell in their body had recorded a message from the prenatal environment. Food is scarce. Store everything you can. But the metabolism is not simply coded in the DNA sequence. Something else had changed. Researchers analyzed the DNA of these individuals, specifically a regulatory region of a gene called IGF-2 involved in growth and metabolism. They found that individuals exposed to the famine in utero had DNA methylation profiles different from those of their unexposed siblings. Methylation is an epigenetic process. It consists of adding chemical groups, markers, onto the DNA without modifying the sequence itself. These markers act like switches. They can turn genes on or off depending on the conditions. They can change how a gene expresses itself without changing what that gene is. And these epigenetic markers induced by prenatal famine were still visible 60 years later in the cells of people who had not been hungry for decades. The body had memorized the famine, not as a conscious memory but as a chemical instruction, as a mark inscribed on the genome by the environment from before birth, and which had never been erased. This is epigenetics in its most striking form. The idea that what you experienced, or what your mother experienced while carrying you, can modify the expression of your genes in a lasting way. But the story goes further, and this is where the terrain becomes both fascinating and uncertain. Some studies have suggested that the epigenetic effects of the hunger winter do not stop at the first generation, that the children of these children of the famine, the grandchildren of the starving women of the winter of 1944, also carry epigenetic traces, that the chemical memory of the famine crossed not one, but 2 generations. This is called transgenerational epigenetic inheritance, and it is one of the most active and controversial questions in contemporary biology. Here is why it is controversial. Classical molecular biology teaches that epigenetic modifications are erased during the formation of reproductive cells, the eggs and the sperm. This is what we call epigenetic reprogramming. The principle is that each new generation starts with a more or less clean slate, without the marks accumulated by the previous generation. This principle is not false, but it is not absolute. Studies on rodents have shown that certain epigenetic modifications escape this erasure and pass from parents to children. Studies on human populations, the hunger winter, but also studies on the descendants of Holocaust survivors and on populations that went through famines in Sweden in the 19th century have provided suggestive data. The word suggestive is chosen carefully because in human biology, demonstrating transgenerational epigenetic transmission is methodologically very difficult. You have to separate epigenetic effects from ordinary genetic effects, from shared environmental effects, from culturally transmitted behaviors. It is a technical and statistical challenge of the highest order. Researchers are honest about this point. The data is promising but not conclusive. The question is open. What is not open, however, is the philosophical implication of this question. If transgenerational epigenetics is real in humans, if the experiences of one generation can modify the gene expression of the following generations, then the boundary between lived history and inherited biology is much more porous than we believed. Think about what that means. Famines, wars, collective traumas. These experiences might not only be transmitted through cultural memory, through stories, through what grandmothers tell their grandchildren around a table. They might also be transmitted in the cells. In the epigenetic markers, in the way certain genes turn on or off in bodies that never lived through those events, but which carry the chemical trace. There is a woman I often imagine when thinking of this story. She lives in Amsterdam in 1944. She is pregnant, perhaps 6 months, Perhaps 3. She stands in line in the freezing cold for a beet ration. She walks home with a few vegetables in her hands, and the feeling that night that she might not have enough strength to finish the pregnancy. But she survives. Her child is born in the spring of 1945. The war ends, food turns. The child grows up, seemingly normal. This woman never knew that she was inscribing something into her child's cells, something chemical, specific, lasting. She was only thinking of surviving, and yet inside the child she carried that night, in the cells dividing and specializing in her womb, something was recording the world. Something was adding markers to genes in response to the famine, in anticipation of a world of scarcity that would never come. Biology does not know that the war is going to end. It prepares the child for the world as it was at the moment of gestation, and sometimes that world was hungry. Tonight, your biology also carries a history. Adaptations to environments your ancestors passed through, epigenetic markers you cannot read, but which perhaps influence at the margins how some of your genes express themselves. You are not just the product of your DNA. You are the product of the history that DNA lived through, and the history your ancestors lived through before you. There is something profound in this idea. Something that looks like memory. Not the memory of words, not the memory of stories we tell each other around a table, but an older, more silent memory, inscribed in the chemistry of cells. And if that memory can cross a generation, maybe 2, maybe more, depending on what science ultimately proves, then evolution is not just what happens in the genes, it also happens in the space between the genes and the world. Let that thought settle gently. The hunger of a woman in Amsterdam, the markers in the cells of a child, the medical data of an adult 60 years later, an open question. All of this is biology taking notes. The famine of the winter of 1944 left traces in cells that were not yet born. But there are more visible, more immediate changes that can be read in our jaws, our arteries, our teeth. Evolutions that happen over just a few generations and that dental surgeons are beginning to notice. Chapter 6. The Tooth of Time. These invisible, chemical epigenetic markers, inscribed in cells that no eye will ever see directly, tell the story of a silent evolution. But there are other, more visible changes that you can almost see by smiling into a mirror. In certain populations of East Asia, Japan, China, Korea, more than a third of adults do not have wisdom teeth. They simply aren't there. Not trapped in the jawbone, not waiting beneath the gums. Absent. And because the gene that commands their development no longer expresses itself as systematically as before, this number is growing, and it is growing faster than most evolutionary biologists would have predicted 50 years ago. Wisdom teeth, the third molars, are a vestige. Our ancestors had larger jaws. They ate hard, fibrous foods, raw or barely cooked tubers, tough meats, unprocessed seeds. A large jaw with a full set of molars was a direct advantage. Wisdom teeth had their place. At the back of a robust jaw, they contributed to chewing foods that required a grinding power our modern foods no longer demand. Then our diet changed. Cooking softened our food. Industrial processing did the rest, and gradually human jaws began to shrink. Not catastrophically, but measurably over hundreds of generations. The problem is that jaw size and the number of teeth are not governed by the same genes. The jaw shrank, the teeth took longer to catch up. Result: millions of people today have a jaw too small to comfortably house their wisdom teeth. Hence the surgical extractions, the orthodontists, the unnecessary pain. It is evolution out of sync, two distinct biological systems adapting at different speeds. But here is what is remarkable. In populations where the jaw shrank earliest and most completely, notably in East Asia, where agriculture and its associated culinary practices are very ancient, the disappearance of wisdom teeth has progressed further, as if selection had more time to eliminate a vestige that no longer provided anything and caused problems. And this process is still ongoing. Recent studies show that the proportion of individuals without wisdom teeth is increasing in many populations and not just in Asia. In Europe, in the United States, and Australia, population dental studies note an increase in the agenesis of third molars. Human dental evolution is measurable today in the records of dental offices. But the jaw and wisdom teeth are not the only anatomical changes documented recently. In 2020, a researcher from Flinders University in Australia, Tegan Lucas, published a study that had an unexpected echo. She had analyzed medical anatomical data on Australian populations covering about 150 years, and she found two strange trends. First trend, the increasing frequency of the persistent median artery. During embryonic development, all humans form a median artery in the forearm. It is present and functional in the early weeks of fetal life. Normally, it regresses and is replaced by other arteries before birth. In most adults, it has disappeared. But since the late 19th century, the proportion of adults who keep it permanently has increased significantly. In the 1880s, about 10% of Australian adults had a persistent median artery. In recent studies from the 2010s, that number approaches 30%. In the span of 130 years, 6 or 7 human generations, the frequency of an anatomical trait tripled in this population. It is a remarkably fast evolutionary pace. Why? We don't know exactly. One hypothesis is that in modern populations, a persistent median artery offers a minor circulatory advantage in certain contexts, perhaps better blood flow to the hand during precision activities. Perhaps selection maintains it for reasons we have not yet identified. Perhaps it is simply genetic drift, a neutral variation that spread by chance. What matters is the fact itself. A human anatomical trait is changing, measurable over less than 2 centuries. Evolution does not just happen in the distant past, in geological strata, in the fossils paleoanthropologists dig up with brushes in the African dust. It happens in radiology rooms, in surgeons' data, in the bodies of people living today. The second trend found by Lucas is even more intriguing. An increase in the frequency of a small extra bone in the foot, the fibella, a sesamoid bone located behind the knee. In the 19th century, the fibella was present in about 11% of humans. Today, it is present in about 39% of people studied across different global populations, an increase of more than 3.5 times in less than 150 years. Here again, we do not exactly understand why. The fibella is associated with mechanical stress on the knee, perhaps changes in average body mass. The biomechanics of walking, or the way we use our bodies, have created an environment in which this extra bone offers a minor mechanical advantage. Or perhaps not. Science has not yet decided. What unites all these stories, the disappearing wisdom teeth, the reappearing artery, the extra bone in the foot, is a simple but profound message. Human bodies are plastic, not just during an individual life, but plastic at the population level, responding to environmental pressures on much shorter timescales than previously thought. Industrial food changed our jaws in a few millennia. Modern lifestyles are perhaps changing our arteries and bones in a few centuries. This is not a dystopia. This is not a catastrophe. It is simply biology. It is what living bodies do. They respond. Imagine a waiting room at an oral surgeon's office, somewhere in New York, in London, in Toronto. There are 5 people sitting with their little folders. 3 of them are there for a wisdom tooth problem, too crowded, poorly positioned, needing extraction. One person has no wisdom teeth at all. They never formed, and the dentist told them this at age 20 as good news. The 5th is a 12-year-old child whose x-rays already show that the wisdom teeth are probably not developing. In this mundane waiting room, with its outdated magazines and bad coffee machine, 4 different stages of human dental evolution are sitting side by side. The species in transition in a waiting room. The night here is quiet. You carry in your mouth a history millions of years old. Molars adapted to grind foods you no longer eat. Perhaps wisdom teeth you will never need, or perhaps their absence, which says your lineage is a little further ahead on the calendar of dental evolution. And in your forearm, perhaps, an artery your great-grandparents did not have. Your body is an archive still being written. Teeth, arteries, small bones. Anatomical evolution is readable in ordinary bodies today, but before these changes were possible, a much deeper upheaval was required. Agriculture, 10,000 years ago, literally rewrote the rules of selection, and the genes followed. Chapter 7. Bread and salt. A reappearing artery, a disappearing tooth. These changes can be read in bodies. But to understand where they come from, we must go back to the most profound transformation the human species has ever gone through. Not in a few centuries, but in a few millennia. The moment someone, somewhere, planted a seed and decided to wait. About 10,000 years ago, in several regions of the world independently, the Fertile Crescent in Mesopotamia, the Yellow River Valley in China, the high plateaus of Central America, the river zones of sub-Saharan Africa, human populations began to do something their ancestors had never done. Cultivate plants, raise animals, stay put. The transition from hunter-gatherers to farmers is often presented as progress, a step toward civilization, toward abundance, toward what would eventually become writing, cities, empires, universities, the internet. And in a very real sense it was. But for the bodies of the first farmers, it was something more ambiguous. It was a shock. The bones of the earliest farmers tell us a story that history textbooks often forget to mention. Compared to the hunter-gatherers who preceded them in the same regions, the first farmers were, on average, shorter. Their bones bore the marks of nutritional deficiencies, lacking iron, protein, and certain vitamins. Their teeth showed much more frequent cavity lesions, the result of a diet rich in fermentable carbohydrates. Their skeletons testified to more frequent infectious diseases, the result of living in high density, close to livestock, in conditions that favored the transmission of pathogens. Agriculture in those early generations was not a luxury, it was a constraint. People transitioned to it because the food supply was more predictable, not because it was better. And in this new environment, this world of density, grains and domestic animals, entirely new selection pressures began to act on the human genome. Take the AMI gene. Salivary amylase is an enzyme you produce in your mouth. It begins to break down starch, the complex carbohydrate of grains, potatoes, and roots, before you have even swallowed your bite. If you chew a piece of white bread for 30 seconds, it will start to taste slightly sweet. Those are the enzymes in your saliva working. Amylase breaks down starch chains into simple sugars. The AMI gene codes for this enzyme. And here is what is remarkable. Humans have a variable number of copies of this gene. Some people have 2 or 3, others have 7, 8, 10. More copies of AMI means more amylase in the saliva and more efficient digestion of starches. And when researchers compared the average number of AMIY1 copies in populations with traditional diets rich in starch versus populations with traditional diets low in starch, they found exactly what evolutionary theory would predict. Agricultural populations have, on average, more copies of AMI1 than hunter-gatherer populations. Agriculture created a selection pressure. Individuals who digested starches better, those who had the most copies of AM1, probably had a slight nutritional advantage in a diet dominated by grains. Over generations, the frequency of multiple copies increased in agricultural populations. This is gene culture coevolution in its most elegant form. A cultural innovation, the cultivation of wheat, creates a new dietary environment. This environment exerts a selection pressure on a gene. That gene evolves in response, and the individuals, carrying the favorable version of the gene, can extract more calories from the foods produced by that cultural innovation, making them slightly better equipped to endure it and develop it further. Culture shapes genes. Genes enable culture. A loop, and this is not an exception in human evolution. It is perhaps the central mechanism of recent human evolution. But agriculture did not only change digestive genes, it changed immune genes. Living in dense villages, cities, and markets where hundreds of people gather regularly creates an ideal environment for the transmission of pathogens. Infectious diseases that could not sustain themselves in small, dispersed groups of hunter-gatherers could suddenly spread in dense, sedentary populations. Smallpox, tuberculosis, measles, typhoid. These diseases likely emerged as major health problems with or after the agricultural transition facilitated by human density and proximity to domestic animals, and they exerted an intense selection pressure. Individuals carrying genetic variants that granted them better resistance to these pathogens survived and reproduced more. Over generations, these variants spread. Populations that lived longest in close contact with certain diseases genetically developed a relative resistance that more recently exposed populations do not necessarily share. This is one of the reasons, not the only one, but a real biological reason why the encounter between New World populations and European diseases in the 5th century was so devastating. Two populations subjected to different selection pressures for millennia with different immune genomes. Colonial history has a genetic dimension that we often underestimate. Agriculture also redesigned the jaw. The jaws of farmers documented in archaeological records around the world are, on average, smaller and less robust than those of their hunter-gatherer ancestors. Soft, cooked ground food required less chewing power. The selection pressure for a large, muscular jaw relaxed. Individuals with smaller jaws were no longer at a disadvantage, and gradually jaws shrank. Not uniformly, not at the same speed in all populations. But the trend is there, and it is readable in the fossils, in dental anthropology, in the dental x-rays of today's clinics. There is a fascinating debate at the heart of this story. On one side, some researchers argue that gene culture coevolution accelerated human evolution, that agriculture, by creating new environments and new selection pressures, produced more genetic change in 10,000 years than a period of the same length would have produced during the hunter-gatherer prehistory. On the other side, other researchers point out that most of these changes are local adaptations, often to specific aspects of the cultural environment and not fundamental transformations of the species architecture. The debated question is, did agriculture make humans more different from one another? Populations adapted to different diets, pathogens, and altitudes. Or did it unify the species by enabling greater population density and thus greater gene flow? Probably both, but in proportions and through mechanisms that population genetics is still struggling to untangle. There is another irony in the history of agriculture and human evolution that I cannot fail to mention. Humans domesticated wheat, barley, rice, corn. But in a certain sense, these plants domesticated us too. They changed our way of life. We stopped migrating. We settled around fields and our societies organized themselves around their cultivation and storage. They changed our diet, less diversity, more carbohydrates, a dependence on a few cultivated species. They changed our AMI1 genes, our immune genes, the size of our jaws. Who domesticated whom in the end? The question is not just rhetorical. It points to something real in evolutionary biology. Evolution is a relationship, not a direction. Wheat benefited from the human as much as the human benefited from the wheat. Both changed under the pressure of the other. Tonight, the bread you perhaps ate for dinner, that slice, that baguette, that piece of biscuit, was broken down by your saliva thanks to copies of AMI that your farming ancestors accumulated over millennia. It is a biological technology, an adaptation inscribed in your mouth thousands of years ago by people who planted grain in fields they would never leave. And in your gut right now, another evolution is underway, less visible but just as real. Billions of bacteria co-evolving with you inside you, whose history is being rewritten by the same cultural forces that redrew your genes. The bread your farming ancestors grew changed your genome. But in your gut, another evolution is unfolding, much faster, much more chaotic, and whose consequences for your health are only just beginning to be understood. Chapter 8. The bacteria in your gut evolve faster than you. Agriculture redrew the genes that digest starch and fight pathogens, but it did not act alone. In your gut, something even more dynamic is happening right now. Something evolving at a speed your genome cannot match. There are about 38 trillion bacteria in your gut. Take a moment with that number. 38 trillion. That is roughly the same as the total number of human cells in your body. You are, in terms of cell count, about half human and half something else. This something else is indispensable to you. It digests what your own enzymes cannot break down. It produces vitamins. It regulates your immune system and communicates with your brain via the vagus nerve. And these bacteria are evolving right now. While you sleep, a gut bacterium can go through a generation every 20 minutes under favorable conditions. A human generation takes 20 to 30 years. In one night of sleep, the bacteria in your gut have had time to go through dozens of generations. It is an evolutionary speed the human species cannot compete with, and since about 1950, since the massive introduction of antibiotics into human and veterinary medicine, we have exerted on these bacterial communities a selection pressure of unprecedented intensity. Antibiotics were one of the greatest medical revolutions of the 20th century. Penicillin, discovered by Alexander Fleming in 1928, put into clinical use during the Second World War, saved millions of lives. Infections that systematically killed, pneumonia, sepsis, tuberculosis, began to be cured in a matter of days. It is a real and immense medical victory. But antibiotics do not distinguish between pathogenic bacteria and useful bacteria. When you take a course of antibiotics, you don't just eradicate the pathogen making you sick. You also disrupt your gut microbiome, the populations of bacteria that have lived in symbiosis in your gut since you were born. And in this disruption, among the bacteria that survive, those carrying antibiotic resistance mechanisms have a massive advantage. They reproduce. They transfer their resistance genes, sometimes even to other bacterial species, through a mechanism called horizontal gene transfer. Antibiotic resistance is bacterial evolution in real time, and we accelerated it. A doctor in a hospital in Paris in 2018, he holds in his hands an antibiogram, a test that indicates which antibiotics are still effective against the bacteria infecting his patient. The list is short, very short. This is what we call a multi-resistant bacterium. In the 1950s, when antibiotics were new, this scenario did not exist. Penicillin killed what it was supposed to kill, and the list of options was long. 70 years of massive use was enough for some bacteria to become resistant to almost all available antibiotics. This is not a metaphor for evolution. It is evolution. Documented, measured, observable on an antibiogram on a Tuesday morning in a hospital room. But antibiotic resistance is only the most dramatic example of a much broader evolution. Our modern lifestyles, ultra-processed food poor in fiber, antibiotics, C-section births, life in sanitized urban environments, are reorganizing our microbiomes in ways we are only beginning to understand. Studies on the microbiomes of communities living traditional lifestyles, hunter-gatherers in the Amazon, rural populations in sub-Saharan Africa, pastoral communities in Central Asia, show a gut bacterial diversity significantly higher than that observed in populations of industrialized countries. This diversity is not an anecdote. It seems to correlate with a different immune health. Autoimmune diseases, allergies, inflammatory bowel diseases, all these pathologies that have exploded in industrialized nations since the mid-20th century seem linked, at least in part, to the impoverishment of the microbiome. Our war against microbes has had collateral damage that we measure in our guts. Here is where the debate is fierce. On one side, some researchers argue that the disruption of the microbiome is irreversible on the scale of a few generations, that we have lost bacterial species that inhabited the human microbiome for hundreds of thousands of years, and that these losses cannot be compensated simply by probiotics or dietary changes. On the other side, other researchers are more optimistic. They argue that the human microbiome is remarkably resilient, that it can reorganize and diversify if conditions allow, and that the microbial diversity observed in populations with traditional lifestyles is not lost, but simply absent under current conditions. Who is right? We do not know yet. Longitudinal studies are lacking, the data is recent, and the microbiome is such a complex system, thousands of species interacting in a space about 6 feet long, that modeling it precisely remains a considerable challenge. What we can say with certainty is that the coevolution between humans and their microbiome is a biological reality of the highest order. These bacteria are not passengers in your body. They are partners, and their evolution is tied to yours. When we started eating differently, our gut bacteria changed. When we started using antibiotics, our bacteria resisted or vanished. When we started being born more and more often by C-section, without passing through the vaginal canal which inoculates the newborn's first microbes, the microbiomes of children born this way began to show different profiles than those born vaginally. Every change in our lifestyle is a change in the evolutionary conditions of our microbial partners, and vice versa. There is something both fascinating and slightly disconcerting in the idea that the most active evolution taking place in your body right now is not in your genome. It is in the 38 trillion bacteria that inhabit you. You are an ecosystem, not an entity, and like any ecosystem, you respond to environmental pressures not only through your own genes, but through the collective genes of all the organisms living inside you. Human evolution is not limited to Homo sapiens. It includes everyone traveling with them. Tonight, while you sleep, the bacteria in your gut are working. They break down, ferment, communicate. Some die, others reproduce. Genes pass from one species to another in the humid silence of your intestines. It is noisy in there, on a scale your body does not perceive. And it is alive, deeply, ceaselessly, furiously alive. In your gut, billions of bacteria evolve in the dark. But outside, another evolutionary force acts on the species. One of the oldest, one of the most powerful, and the one we most often forget to name, choice. Chapter 9, The Selection We Don't See. Those bacteria evolving in the silence of the gut, they evolve because conditions change, because resources are there or lacking, because selection pushes them. But there is an evolutionary force acting on the human species that is just as ancient, just as powerful, and infinitely more intimate. Every time someone chooses a partner, they participate, without knowing it, without intending to, in the evolution of the species. This is not a metaphor, it is mechanics. Sexual selection is one of the two great evolutionary forces identified by Darwin. Natural selection, which operates on survival, and sexual selection, which operates on reproduction. It is the partners individuals choose, and the traits those choices favor, that shape a part of the species' evolution. In other animal species, sexual selection produces spectacular and sometimes absurd results. The peacock's tail, so heavy, so flashy, so disadvantageous for fleeing predators, exists because peons find it attractive and prefer males who have a large one. The tail does not help the peacock survive. It helps the peacock reproduce, and sexual selection only cares about reproduction. In humans, sexual selection is more complex and more discreet, but it is no less real. The question of what makes a partner attractive in the eyes of a human being is one of the most debated in evolutionary psychology, and it is delicate because it touches on subjects where biology and social constructs are difficult to untangle. What cross-cultural studies robustly seem to indicate is this. Certain signals of health and fertility are widely perceived as attractive across cultures. Skin without severe lesions, a certain facial symmetry, indicators of physical vigor and energy. These signals can biologically translate to infection resistance, genomic stability, good general health. What is less clear is how specific preferences vary considerably across cultures, eras, and economic contexts. What was considered attractive in medieval Europe, in Tang Dynasty China, in nomadic steppe societies, or in today's megacities is not identical. The evolutionary foundation and cultural expressions overlap in a way science is still only imperfectly unraveling. But what matters for evolution is not so much what individuals find beautiful, it is who reproduces with whom, and in modern human societies, mating patterns have changed in a way that creates evolutionary pressures our Pleistocene ancestors would not have recognized. In modern industrialized societies, people tend to choose partners who resemble them across measurable dimensions, education level, socioeconomic status, political and cultural values, sometimes geographic or ethnic origin. This phenomenon is called positive assortative mating, and it has genetic consequences. If individuals with a certain profile, say a high level of education correlated with certain partially heritable cognitive traits, preferentially reproduce with each other, then the children of these unions will have a higher chance of carrying the genetic variants associated with those traits. Over generations, this can amplify genetic differences between social groups. This is not eugenics. No one planned this. It is simply sexual selection operating within the current social context, with consequences we poorly understand and do not control. There is an uncomfortable tension in this idea. On one hand, the freedom of romantic choice is a fundamental value. Choosing your partner according to your own criteria, whatever they may be, is an expression of individual autonomy. On the other hand, this choice, aggregated across millions of individuals over generations, is a real evolutionary force. The collective preferences of a society slowly shape the traits that reproduce the most. It is neither good nor bad. It is simply true, and it is a truth that should humble our intuitions about human evolution. Because one of the most powerful evolutionary pressures on the species is not disease, nor famine, nor climate change. It is desire. There is another dimension to modern human sexual selection that is often forgotten. New reproductive technologies. Contraception, by allowing people to separate sexuality from reproduction, has radically altered reproduction patterns in industrialized societies. People no longer have children as a default consequence of sexual activity. They have them when they decide to. And this decision, influenced by economic, cultural, and educational factors, but also by biological factors like individual fertility, the disposition to want children, and hormonal timing, is itself a selection pressure. Individuals who naturally have the desire to have children early, and who have the conditions to do so, have more children in modern societies than those who have children late or not at all. If these dispositions are partially heritable, and behavioral genetics studies suggest they are to some extent, then contraception, paradoxically, may be modifying the allele frequencies associated with reproductive behaviors. Evolution once again follows behaviors, even the behaviors we invent. Tonight, somewhere in the world, two people are meeting. They do not yet know if they will have children together. They do not yet know what future they will share. They are certainly not thinking about the evolution of the species. And yet, if they have children, if the genes of one and the other mix in a child yet to be born, they will participate, like millions of other couples on the planet, in the slow sculpting of the collective human genome. Neither of them chose this. Neither of them can be held responsible for it. It is simply how evolution works, in the encounters, in the desires, in the ordinary decisions of an ordinary life. This thought has something dizzying and calming at the same time. Dizzying because it says we do not control our own evolution, that it unfolds in our choices without us knowing it. Calming because it says evolution is not a program, not a destiny, not a march towards something. It is simply the sum of all these moments, these encounters and desires, these children added up over generations. And in that sum, there is something unpredictable and alive. But if human evolution has always proceeded blindly, without intention, without direction, through the accumulation of micro-decisions and environmental pressures, one man in November 2018 decided to do things differently, to intervene directly, to deliberately rewrite the genome of human beings who were not yet born, and the world did not agree on what that meant. The romantic choices accumulated over generations imperceptibly shaped the species. But in 2018, in a laboratory in southern China, someone decided to stop waiting for the silent accumulation of time. He took genetic scissors and he cut. Chapter 10, He Jiankui and the Children Who Shouldn't Have Existed. Human desire shaping evolution without knowing it. That ancient blind force accumulated over millions of nights just like this one. And then suddenly, someone who decides the wait is over. In November 2018, for the first time in the history of the human species, two human beings were born with a genome deliberately modified by another human being. Their names are, or were in the pseudonyms given by their creator, Lulu and Nana. They grew up somewhere in China. In anonymity, we hope. In good health, we also hope. Although no one is entirely certain. He Jiankui was 34 years old when he did what the global scientific community forbade him to do. A biophysics researcher at the Southern University of Science and Technology in Shenzhen, partly trained in the United States. He worked on genomic editing techniques, specifically CRISPR-Cas9, the technology that allows you to target a precise DNA sequence in a living cell and cut it, modify it, replace it. CRISPR-Cas9 is often described as molecular scissors. It is not entirely exact, it is more precise than scissors. But the image captures something true. It is a steerable cutting tool with remarkable precision. Imperfect, but remarkably powerful. He Jiankui used this tool on human embryos produced by in vitro fertilization from parents where one was an HIV carrier. His stated goal was to delete the CCR5 gene in the genome of these embryos. CCR5 codes for receptor present on the surface of certain immune cells. HIV uses this receptor as an entry point into the cells. It exists in only a tiny fraction of the population naturally, less than 1%. A mutation that completely deletes CCR5, and the people who carry it are largely resistant to HIV infection. He Jiankui wanted to confer this resistance deliberately. He wanted babies that HIV could not infect. 2 embryos with a genetic modification were implanted. The pregnancies went to term. Lulu and Nana were born. Picture He Jiankui, alone in his lab at night, a few months before the story breaks. He knows what he has done. He knows his modification worked, at least partially. He also knows that the twins' genomes are not identical to each other. The modification took differently in the 2 cases, leaving one with a complete deletion of CCR5 and the other with a partial deletion. He knows the scientific community will react with horror. He is convinced, or wants to be, that he is acting for the greater good, that he is protecting these children from a devastating disease, that he is forging a path toward eliminating genetic illnesses. And he keeps silent for a few more weeks. Then, on November 25, 2018, the MIT Technology Review breaks the story. The international reaction was immediate and universally condemning. Nobel laureates, geneticists, and ethicists from all over the world, people who dedicated their lives to developing these very technologies, denounced the experiment as irresponsible, dangerous, premature, and ethically unacceptable. There were several technical reasons. First, the deletion of CCR5 is not without risk. CCR5 plays other biological roles, not just as a gateway for HIV. Studies have suggested that people naturally lacking CCR5 may be more vulnerable to certain other infections, notably West Nile virus and certain flus. Eliminating it deliberately in an embryo, in a context where the long-term effects were unknown, was taking an unconsented risk on beings who had not asked to be modified. The technique itself presented risks of off-target effects, unintended modifications of other genes. In adult cells, this risk can be monitored. In an embryo that will develop into a complete human being, every single cell inherits the modification and any unforeseen effect, and above all, He Jiankui had not waited for the scientific and ethical consensus on human germline modification to be established. He had acted alone, in secret. He was convicted in December 2019 by a Chinese court. 3 years per prison, a fine, a permanent ban from working in universities or laboratories. Lulu and Nana, they are still living. They asked for none of this. This story raises a question that science alone cannot resolve. At what point does the deliberate genetic modification of a human being become a new form of evolution, a directed intentional evolution, taken in hand by the species itself, and who decides? He Jiankui claimed to decide for 2 children. The scientific community said that no one, and certainly not a researcher acting alone in secret, should have that power. And behind the universal condemnation of what he did, there is a harder question about what is permissible, because the genetic modification of human embryos is not inherently condemnable in all ethical systems. Certain genetic diseases, Huntington's disease, Duchenne muscular dystrophy, sickle cell anemia, cause immense suffering. If the technique were safe, if a consensus existed, if the ethical and regulatory frameworks were in place, would it be acceptable to intervene on an embryo's genome to prevent a lifetime of pain? Most bioethics researchers answer perhaps. For certain severe diseases, within strict frameworks, with appropriate consent, after an international consensus. It is not the same thing as what He Jiankui did, but it is in the same conceptual space. And beyond severe diseases, there is another frontier, even more difficult. Modifying a gene to prevent a disease, we can call that medicine. Modifying several genes to enhance a capability, intelligence, resistance to aging, physical performance, that is something else entirely. That is where eugenics, that bloody specter of the 20th century, resurfaces in a new form. Not imposed by a state, but potentially chosen by parents who have the means to pay for their children's modification. A society where some children would be genetically modified and others would not, where biology would be, for the first time in the history of the species, directly linked to the wealth of the family you are born into. This is not science fiction. These are the questions that ethics committees all over the world are debating right now, in 2024, in 2025, in conference rooms in Geneva, in Paris, in Beijing. What He Jiankui opened was not an answer, it was a question. The same question that evolution has always posed to the human species, but in a new way, more urgent, more directly in our hands. We have always been the product of forces we did not control. Random mutation, blind natural selection, unlikely encounters with other human species in Siberian caves. famines that write chemical instructions into the cells of unborn children. Now, for the first time, we have a tool, an imperfect tool, a tool whose full effects we do not master, a tool that has already been misused, but a tool nonetheless. Lulu and Nana are growing up. They carry in every cell of their bodies a modification that no one before them carried, a modification no one asked them to bear. They did not choose to be the first, and they perhaps do not yet know what they are. He Jiankui cut into a human genome with molecular scissors. 2 children carry that mark, and the whole world now wonders what comes next, what we want to do with this capability, and what our decisions today will leave in the bodies of those who come after us. Chapter 11. What our descendants will carry from us. Lulu and Nana are growing up somewhere with their modified genes, the first of their kind, without having chosen it, and the question they carry without knowing it is the same one that every generation has carried silently since the first Homo sapiens. The same question, but for the first time asked directly. What are we going to leave behind? We have traversed, throughout these chapters, a dozen stories. A glass of milk, a pinky bone in a Siberian cave, a shrinking brain, a woman in Framingham whose medical data proves evolution is underway, a starving mother in Amsterdam whose unborn child's cells recorded the famine, disappearing wisdom teeth, digestive genes multiplying under the pressure of agriculture, gut bacteria evolving faster than we do, desire-shaping genes without knowing it, a researcher who decided the wait was over. All these stories say the same thing. Human evolution has never stopped. It never had a pause, never had a finish line, never planned a moment when the species would be complete. It responds, it adapts, it changes according to what is there. Diseases, foods, altitudes, choices, technologies, accidents. And what we are doing now, the decisions our societies make, the technologies we deploy, the environmental pressures we create or endure, are the conditions in which generations to come will evolve. Here are some of the selection pressures acting right now on the human species, or that could act in the decades to come. Climate change is creating new environmental conditions. Higher temperatures in certain regions, droughts, floods, the reorganization of ecosystems. These changes will affect the distribution of infectious diseases. Certain vectors, like mosquitoes carrying malaria and dengue, are expanding into latitudes they had never reached before. New selection pressures on immune genomes. Antibiotic resistance is an evolutionary crisis in real time. If we do not develop new therapeutic strategies, bacterial infections could once again become a major cause of mortality in the coming decades, which would recreate a selection pressure for immune resistance that 20th century medicine had partially alleviated. Urbanization is concentrating more and more humans in dense environments with diets, levels of pathogen exposure, and lifestyles radically different from those in which the species evolved for most of its history. These environments create new pressures, and perhaps select for traits adapted to urban life that we do not yet know how to identify, and genetic engineering. That open question, still without a stable answer. What is certain is that the ethical and regulatory frameworks for modifying the human genome are being drafted. In 2020, an international committee of experts, convened by the National Academies of Sciences of the United States and the United Kingdom and by the Chinese Academy of Sciences, published a report concluding that it would be irresponsible to proceed with heritable germline modifications in humans before very strict conditions are met. Notably, a much better understanding of the off-target effects of CRISPR and a broader social consensus on acceptable goals. This report does not close the door. It says not yet, not like this. And in laboratories, researchers continue to work on CRISPR, on other even more precise editing systems, on gene therapies that modify somatic cells, the cells of the adult body without touching the germline. Therapies that heal without modifying what will be passed on. The boundary between healing and modifying the species has not yet been crossed, but it is under active discussion. But there is something important to say here, something that evolutionary biology states clearly, and that debates on transhumanism sometimes forget. Modifying a gene does not modify a species. The species is a population, a distribution of genetic variants across millions, billions of individuals. Modifying a few embryos, even deliberately and systematically over several generations, only takes control of evolution in a very limited sense. Genetic drift, spontaneous mutations, migratory flows between populations, unpredictable diseases, climate changes, all of this continues to act. Evolution is not a machine you can steer. It is a process that you can disrupt, partially guide, locally accelerate, but which always responds to forces we do not entirely control. Even with CRISPR, even with the most advanced biotechnologies. What is human in this matter is precisely this point. We are the species that can think about its own evolution, debate its own evolution, make decisions that affect its own evolution. but we are not the species that can stop or totally control the process. We are inside it, as we have always been. Here is a question I would like to leave you with. If you could modify a trait in the genome of an unborn child, eliminate a disease, confer a resistance, enhance an ability, would you do it? And if so, who decides what is a disease and what is simply normal human variation? And who decides what is an enhancement and what is a homogenization? Who decides the limits? These are not rhetorical questions. These are the questions that ethics committees, governments, philosophers, patients, parents, and doctors are debating right now across the world. And your answer, your personal answer tonight, is part of that debate, even if you don't know it, even if you don't sit on any committee. Because societies eventually reflect the intuitions of their members, and the laws those societies will write about human genetic engineering in the coming decades will partly be the reflection of what millions of people think tonight about these questions. I want to finish with something small. There is a child somewhere in the world tonight. Perhaps in New York, perhaps in London, perhaps in Cape Town, or in Sydney, or in Los Angeles, in any of the places where this voice travels. Perhaps they are already asleep. Perhaps someone is reading them a story in a low voice in the dark. In every cell of that child, there is a genome, a text of 3 billion base pairs, copied from an egg and a sperm that found each other at a specific moment in a specific life. In that genome, there is perhaps a variant of AMI1 inherited from ancient farmers, perhaps an immune variant that comes from an encounter between an ancestor and a Neanderthal 40,000 years ago, perhaps epigenetic markers carrying the trace of a famine, a hard winter, a moment of hunger in a forgotten life. This child knows nothing of all this. They simply sleep, and in that sleep, evolution continues its silent work. Mutations accumulate in someone's germ cells, somewhere. Mutations of which no one yet knows whether they will be neutral, favorable, or unfavorable. Populations migrate, mix, pass on genes that no one chose. Selection pressures exert themselves in directions we might only understand in 1,000 years. The species is in motion. It has always been in motion. The question of the title of this documentary, Why Humans Stopped Evolving, was a trap built from a deeply widespread and deeply false intuition. Humans have not stopped evolving. They are evolving differently, under new pressures at rhythms that vary according to populations, environments, cultural practices, with epigenetic, microbial, and technological mechanisms that Darwin had not foreseen, and that we still only imperfectly understand. But evolution, it does not wait for us to understand it. It continues. In the Neander Valley in Germany, there is a museum dedicated to the Neanderthal, the human being whose bones were discovered there in 1856, and who gave their name to an entire vanished species. At the museum, there is a reconstruction of what a Neanderthal might have looked like. Tall, robust, prominent forehead, a gaze looking straight ahead. He does not look like someone else. He looks like someone you know, someone you could have crossed paths with on a street, if the 40,000 years of separation had not existed. And to a certain extent, you have crossed paths with him, because he still lives in your cells. Not him, but something of him. A DNA sequence that survived his disappearance, carried in the bodies of his hybrid descendants all the way to you. You are partly the child of someone who no longer exists, and your descendants will be partly the child of something we cannot yet imagine. Tonight you are listening to a voice in the dark. Humans have always done this. Even before having a complex language, even before having words for the things they wanted to tell each other. They gathered in the darkness. Someone spoke and the others listened. The vigil, that moment when the day stops and the story begins, is perhaps as old as the fire in the caves, around the embers under the stars of a sky without artificial lights, in houses closed against the winter, and now in a bedroom somewhere in the English-speaking world, with a voice in an earpiece or on a phone resting on a nightstand. The form has changed, the gesture is identical. If this journey spoke to you, if you now carry a question you didn't have last night, I am genuinely glad. Subscribe if you want other nights like this one to keep arriving. Leave a comment to tell me where you are listening from. New York, London, Toronto, Johannesburg, Sydney, or anywhere else in the world. I read these messages, they matter, or do none of that. Just close your eyes. There is a child sleeping tonight. In every cell of their body, a genome waits. It doesn't yet know what it will carry. It doesn't yet know what it will leave behind. It simply sleeps. And evolution, it watches in silence just as it always has.